Okay, referring back to the previous video, we're going back to our search for delta. In equation 1, and that's where we stopped, we had the absolute value of f of x minus L is equal to the absolute value of x squared minus 4, which we factored down to absolute value of x plus 2 times absolute value of x minus 2. And that is smaller than 5 times the absolute value of x minus 2. And the reason why is because we put a bound on x plus 2. 5. It's smaller than 5, so we replace it with 5 with the inequality sign. But that is less than 5 times delta, and that's because we made the assumption that the absolute value of x minus 2 was smaller than delta. Okay, but the problem is that we want the last thing on that line to equal epsilon. So take that stuff at the end, 5 times delta, set it equal to epsilon, and then solve that for delta to get the delta that we need to do our proof. Okay? So we have delta equals epsilon over 5. Okay, so we have at this point one restriction on the absolute value of x plus 2. It is specifically the absolute value of x plus 2 is smaller than 5. That's a bound that we found. And we had two restrictions on the absolute value of x minus 2. The first one came in the previous video when we said, well, let's choose a value for delta. Let's say the absolute value of x minus 2 is smaller than 1 because it has to be really small. Well, making that assumption, we have to be careful and respect that, but there's also the assumption that in general it's less than delta, and here we've actually established delta to be epsilon over 5. So we have to be certain that both of these restrictions on the absolute value of x minus 2 are met. To do that, we're going to bound parenthesis x minus 2 within a smallest interval by saying let delta equal the minimum value between these two values, 1 and epsilon over 5. That way we were respecting both of these restrictions on the absolute value of x minus 2. Okay, so step 2. We're going to assume the absolute value of x minus a is smaller than delta and choose for this case delta equals the minimum between 1 and epsilon over 5, then show by substitution that the absolute value of f of x minus L is smaller than epsilon. So proof, assume that x minus 2 absolute value is smaller than delta and absolute value of x plus 2 is less than 5 because we found that bound, and let delta equal the minimum between 1 and epsilon over 5. Now figure out what the absolute value of f of x minus L is. Remember, we want it to end up being smaller than epsilon. So here's what we've done so far. We're just repeating this work, absolute value of x plus 2 times absolute value of x minus 2. Turns out that's less than 5 times delta, and the reason is that we made that assumption that x plus 5 absolute value at the star location is where we did it. It's smaller than 5. Okay, and that delta is actually there because we made the assumption that the absolute value of x minus 2 is less than delta. Now we can go one of two ways depending on whether the minimum value for delta is 1 or epsilon over 5. First, consider it being epsilon over 5. In that case, we replace 5 times delta with 5 times epsilon over 5. The 5's cancel. That's equal to epsilon. Everything's good. Other possibility, what if the minimum between those two values, 1 and epsilon over 5, is actually 1? Well, in that case, we will have that 5 times delta equals 5 times 1. 5 times 1. Okay, well that means it's equal to 5. But we want it to be less than epsilon. Is it really going to be less than epsilon? Well, actually, yes, because if we chose the minimum between 1 and epsilon over 5 to be 1, that means epsilon over 5 is larger. It's larger than 1. And if you solve that inequality for epsilon, you get epsilon greater than 5. If epsilon's greater than 5, which we're seeing here, that means that the 5 that we had at the end has got to be smaller than epsilon. And all is good in either case. Thus our conclusion is that the limit as x approaches 2 of x squared is equal to 4.